we took out the word child from the title because we thought that might put people off. But it's a very simple method. We came up with an algorithm for for computing the coordination sequences and for proving that they are what we think they are, what they should be. And then we apply it, and we solved the one on the poster and all the other ones that were many of the other ones. And the technique, so the idea is we have a graph and we've got a distinguished point and we want to keep track of how many vertices there are in each shell around it. These are the contour lines. And what we do is we find a special kind of subgraph. We don't really have an official name for it, but it should have some properties that every vertex should be connected to the base point through the subgraph. And these paths should be as short as possible. There shouldn't be any shortcuts. If you want to go from here to the base point, you may as well follow our path. In this case, it's a tree, and a tree is always a good idea, but not always optimal. So we say, we think of this, we use arboreal notation, that we have trunks, which are in blue, and they're like the main lines. And then we have branches coming out of the trunks. And sometimes we have twigs, because the branches don't always meet all the vertices. So much again. And there are a couple of other properties. It should be obvious that there are no shortcuts, and it should be easy to count the number at each distance. And so we did that for the Cairo tiling. This is the way we handled the Cairo tiling for a tetravalent node, a degree 4 node. And here is our graph. There are 4 trunks, and then there are these green branches. And we have to prove that it has the properties that I said. And you can do that by straightening out the blue trunks. And then you can see that there are no shortcuts, and you can see that each step you get one more vertex at each degree. So that proves that the total number is 4n, just as it is for the square grid, and solves the problem for a tetravalent. And then we did it for a trivalent node, a degree 3 node. And now it turns out the nicest way to do it is to have 6 trunks in blue, 2, 1, and 1. And in order to reach some of the intermediate things, we have twigs. The twigs are bounded little things that grow off the branches. And so we were able to get a recurrence for the number. And we did that for a number of others. There are, in fact, 11 regular tilings in 2 dimensions. These are the famous Archimedean tilings. These have the property that every point is as good as every other point. The group is transitive on the vertices, and all of the tiles are regular polygons. So, for instance, the square grid is called 4 to the 4th, because around each point we have 4 squares. This is 3 to the 4th 6, as on the postcard, on the poster, and so on. This is 3 squared 4, 3, 4. This is actually the dual to the Cairo tiling in the graph theoretic sense. That's the first 6 of them, and there are 5 more. And we applied our method to all of these and made sure that all the assertions about the coordination sequences in the OEIS were correct. There were several conjectured ones that we took care of. And then we did a whole lot of others. And sometimes for the more complicated ones, we had to use a third concept from tree growing called a burl. The burl of a tree is something that a lump that sticks out like that. So, for example, in order to handle the 33434, the dual to the Cairo tiling, we have 4 trunks, but 2 of the trunks have burls in them. That's another example. And then those were the 11 uniform tilings. There are also 20 tilings where the group acts doubly transit. It has 2 orbits on points. So there are 20 tilings, like the Cairo tiling, where the group has 2 orbits. There are 61 tilings where the group has 3 orbits. The tiles must always be regular figures. So that's a sequence that Brian Gullebach has computed. The number of K uniform tilings from K up to 6. And with some help, I worked out the coordination sequences for all of these. There are a total of 6,500 coordination sequences, empirically, just getting the first 100 terms or so. So, there's a lot of open questions here. When you're studying these coordination sequences, you go through the following steps. You first of all want to know what are the initial terms, what are the numerical values. Secondly, you look it up in the OEIS. And if it's there with a formula, good. If it's not there, then it gets interesting. So then you look for a generating function. You try to guess one using GFUN in Maple. And for that, works most of the time. Maybe you need 100 terms to do it. Then you try to prove the generating function is correct. And we've only done that for the 1 transitive, partly for the 2 transitive, for the 2 orbit ones. And I should say that our coloring book method, it's not really an algorithm yet. It would be nice to have a formal process for doing it. There are a lot of different kinds of tilings. And here's an example of one. There's a database called the RCSR, Reticulated Chemistry Structure Resource, which has thousands of nets and crystals in 2 and 3 dimensions. So here's an example called the KRT net. And that's what it looks like. If you look it up in the RCSR database, it will give you the 2 coordination sequences, the first 10 terms. There are 2 kinds of vertices, but it doesn't give formulas. So for this particular one, Joseph Myers worked out 1,000 terms. And using the 1,000 terms, we could guess a generating function. This is an open question.
Right.
Is there a proof?
You don't need 1,000 terms, probably 20 even now.
Yes. But to be safe, it's nice if 1,000 terms it works. It gives you more confidence.
It's proving
Because-
up for me, is it?
Well, yes. And probably you wouldn't, but would you, I would like a proof of this. But this is just one of a very large number.
But it is possible to prove it for the whole class, it's always a rational cellular function?
I'm coming to that. No, I don't know that. That's a very good question coming up in a minute. Yeah. So the question is, if you have a periodic tiling, does it have a rational generating function? There are many tilings. If you look at images of tilings on the web, you'll see lots of beautiful ones.
But so far, it's all do. The one you know.
Sorry?
So far, everything you have has either proven or conjectured rational generating function.
For the 6,000 ones, the K transitive, the K uniform ones, no, we don't have generating functions for most of them. I think. Not sure. What about aperiodic tilings? So here's the Ammann-Benker tiling, which is a bit like the Penrose tiles. It has a tenfold, it has a point with 8-fold symmetry, a distinguished point. So you could look at the coordination sequence with respect to the distinguished center. And Remy Seacrest worked out the beginning of the coordination sequence. We have 900 terms, we have no generating function.
Oh, so this may be a counterexample.
It's not periodic. The conjecture is, if it's a periodic structure,
periodic.
then it has a rational generating
Oh, but
function.
periodic.
But this is definitely non-periodic, like the Penrose tiles. They can't be periodic because they've got the wrong kind of symmetry. Another question is the limits of the contour lines. There's some interesting work that I haven't followed. I do want to mention the Knight's move, Ulam-Warburton. So here's the classical Ulam-Warburton automaton. And you're on graph paper, you start with one cell that's on, and you get turned on. If exactly one of your neighbors is on, you get turned on. So one turns on its 4 neighbors, now we have 5. That turns on, learns 4 neighbors, you have 9, and so on. So this is classical Ulam-Warburton. The new one is the same thing, except you use a Knight's move. So it's a little hard to see the graph paper. You start here, you turn on that. In one step, you turn on 8. And then in 2 steps, you turn on 8 more. So you go from 1 to 9 to 17. And the question is, what are those 2 sequences? And the pictures, so I don't know if you can see this. This is a drawing that Remy Seacrest made. In that each of the initial points are joined to the 6 neighbors that are turned on. So you can see it's got a very beautiful structure, which becomes more beautiful if you look at, this is I think 255 generations. What is this? It would be nice to have some kind of formula. Because there's a simple formula for Ulam-Warburton, maybe this has a simple formula too. In any case, it's something to admire. And, oh yes, so this sequence I started off with, what's the explanation? Did anyone guess?
I already know.
You already know.
Last
So
time,
that's
yeah, you mentioned.
yeah. So the rule, okay, so we go back. Okay, the rule is you throw away any number, any digit that's duplicated. So when we're going along, we keep doubling. This is the sequence where you start with 1 and you keep doubling it, and whenever you get to a number that has repeated digits, you throw them away. So when we got to 61, we doubled it, and we got 122. But the 2 appeared twice. Let's throw them away. We get 1. So 61 goes to 1. That's why 32768 goes to 65536, right? 2 to the 16. But 65536, we've got 2 6s, kill them, 2 5s, kill them, you're left with 3. And that's the sequence. It's periodic and period, whatever it is.
So how about that now? Only kill adjacent duplicated digits.
Sorry?
So only kill like the 5 because they are adjacent. What about this rule? Any sequence on the this rule?
I don't understand. Maybe ask me
You can
afterwards.
suggest that instead of casting out duplicates, generally you only cast duplicates which are adjacent.
Yeah.
Ah, yes, yes, yeah, okay. Could be a new sequence. I didn't look at it. I mean, there were other questions. This was again a sequence from Eric Angelini, this throwing away duplicates, and he was interested in various things. The graphs, by the way, of the sequence. What happens if you start with n, the binary expansion of n, and apply this operation? The graph looks like this. If you go 200 terms, and if you take 10,000 terms, it grows so fast you have to take logs, and you get a very interesting looking graph. There's a question, a sequence from Alan Wechsler, which is, I was thinking that one of the grad students who has been looking at partitions might be interested in this. It's the following question. Take n, how many ways are there to partition it into parts that are consecutive, except that the last part can appear more than once? So, how many ways are there to partition 9? Well, you could do 1 and 8, but 1 and 8 are not consecutive. You could do 4 and 5, and that's legal. You could do 9, but the rule is the parts each part must appear just once, except the largest part can appear any number of times. So we could have 1 9 times. The largest part is 1 and appears multiple times. Or we could have a 1 and a 2 and 2 3s. So the parts are consecutive, and the largest part can appear more than once, and all the other parts must appear exactly once. How many ways are there? And the amazing thing about this is the graph is so messy, because most of these similar kinds of things, like the number of partitions into consecutive parts, is just a number of odd divisors. It's messy, but it's not. It is messy, but most partition questions are nowhere near as nasty as that. And I wanted to thank all the editors who keep the OEIS running. These days we get so many submissions that it's very hard to keep track, to keep up with them. We often have 300 or 400 submissions waiting to be processed. We need more editors, and it's always interesting work. And those are some of the main editors who keep us running. We need more of them. And as I said here, there's no pay, but lots of fun. And you can work as much as little as you like. And if you're interested, get in touch with me. I think that's the end.
Thanks for all these great comments. We'll be glad to answer questions. Thank you.